Hi guys, and so I know there's no one here yet, but I'm going to need to use S7, and so I'm going to start us off with a review for what this exam will cover. In terms of chapter 3, it's going to review a lot of your 2D kinematics, and this is going to involve your motions in your X and Y axes, and this is probably going to likely include drawing motion graphs representing that motion, whether it's in the X or Y direction, and also could include result in a vector addition, whether that's like directly testing you on that addition and subtraction, or it's going to integrate it into your kinematics, right? And then next, you're going to have chapters 4 and 5, which I think are like the big dogs, right? These are your forces and all the laws of motion. And so this is going to include being tested on how to draw a three-body diagram, how to find net forces, and how to, from those net forces, be able to find acceleration. And this all comes down to learning how to identify your systems. And there's a little bit at the end on how to find coefficient of friction or just a friction force in a certain object, or how to deal with irregular systems, right? Non-perfect systems. So I think we'll start off with a review for chapter 3. A lot of this is just 2D, right? And so of course you have your core component equations. I'm taking this from off the internet, but of course you use what works for you. So personally, I never think of it in terms of X and Y because I always think like, I use the same equations. But I'm going to split it up for y'all so that if you're referring back to this, these annotated slides, you'll be able to see kind of how they work if you have any questions on that. So I always think of it as 4 kinematic equations. In your X component, you have your X velocity in the horizontal is equal to initial vertical velocity plus acceleration of that vertical velocity. I just said first vertical. I meant horizontal velocity. Okay, scratch all that. I'm just blubbering at this point. So we're going to start off with our equations in the X direction. And this is going to be starting off with this equation right here, which starts off with your final velocity in the horizontal direction is equal to the initial horizontal velocity plus acceleration in that horizontal direction times time. And you also have x is equal to half initial horizontal velocity plus final horizontal velocity times time. And then you have, trying to see what this says right here. Okay, I can't. So go enlarge it. Maybe not, maybe they just don't like me. Okay. I can't read that because the little camera thing is blocking it. But it says final position is equal to initial horizontal velocity times time plus half acceleration in the horizontal component times time squared. And then I'm tired of yapping, so I'm just going to continue writing it down. But you get the method, you get the madness, right? It's all this that you've seen before when you were dealing with 1D motion. But now that we're not only just going to have it in one component, we're going to have it in two. And so you're going to have your, what we call our Y equations, right? So this is dealing with any kind of motion that goes this way. And this is going to be dealing with motion that goes this way. And so all that is that you're just going to replace all your X's with Y's, right? You're now thinking about things as they are moving up and down instead of how that object is moving across. And as you see, they're pretty much the same equations. You can include them, you cannot include them, up to you. Okay. So I think the most important things for this unit is really understanding what's happening in a projectile across and up and down. Okay. And I think there's like a few core things to understand. You're good. Which is, for example, in this sample projection right here, we have a motion like this, right? This is an ideal projectile. What we do is we start off this motion. I'm going to do the X and Y motion in red. So think about it as you're throwing the ball, right? And try to actually turn on my video. As you're throwing a ball, as you're throwing a land or anything, I'm trying to find something light to throw. If you see it, you start off pretty slow. You start pretty fast in terms of if we're only thinking about things going up and down. You start off pretty fast, right? Because you need all that oomph to kind of get it into the air. And so we start off with a lot of vertical motion that kind of decreases as we reach the peak until it's going to be zero at the top. So Vy final is equal to zero at the top. And then, when you're going downwards, this motion is going to be corresponding with acceleration. And so because we have it going the same direction as gravity, right? As gravitational acceleration constant, it's going to be speeding up, right? We have a little arrow, but it's going to speed up the closer it gets to the ground because it's going in the same direction as the acceleration constant, which means it's accelerating. So that's good to know about our vertical component. In our other way, we have our horizontal component. And what's important for you to know about this in terms of, this is our velocity, right? But what's important for you to know about the horizontal component of velocity of a projectile is that it stays the same the entire time. So the entire time, for example, if we start off at 3 meters per second, we're going to end at 3 meters per second. At the top, it's going to be Vx is equal to whatever, right? So this Vx initial is going to be equal to this Vx final. And I think these things are really important. And so when we're talking about acceleration, right? If I was thinking about this motion in terms of an acceleration graph, really, we only have to think about two things, right? Actually, I don't think I need to draw that for you. I think what you need to know is that acceleration, because you can see how when we're going up and down, these up and down arrows, they're decreasing at the top. It's because acceleration is always pointing downwards, and it's always going to be negative 9.8 meters per second squared for vertical, aka y-axis, okay? And in your horizontal, aka your x, it's always going to be zero because when we think about something that is moving at the same velocity the entire time, there is no acceleration because it's neither speeding up nor slowing down. So acceleration is always going to be 0 meters per second squared. Okay. And so these are kind of important things to look at and to understand conceptually before we start solving these problems, to kind of breaking them down. All right. So with that being said, that was a really brief review. Actually, I think one more component I'm going to review is our position and time graphs, which just briefly, which you've already done, right? And so you have, your position versus time. You have your velocity versus time. And then you have your acceleration versus time. Still brush up on these graphs just in case you test them. Just know that it goes like that, okay? Just know the trends. I'm not gonna spend too much time on it because this should have been something you covered in your first exam, but take some time to review it. And this review itself will actually cover that review as well. Okay, so let's start off with our first review problem of today, which is a cannonball is fired with an initial speed of 40 meters per second. Let's highlight that. Initial speed and a launch angle. Why is it spazzing out? Of 30 degrees from a cliff that is 25 meters tall. So my little note says that it's a 5-part question, but let's answer the first part, which is what is the flight time of that cannonball, right? Just give me a second. I'm gonna adjust. Okay. So what I'm gonna do first is I'm gonna first draw a picture of what they want me to draw, which is I know a cannonball is being fired from a cliff of a certain height at a certain degree. So I'm gonna draw my picture. I want to be able to understand what's going on. Take a sip of my Coke. We've got it here. I'm gonna draw a picture. Let's try to understand what's happening before we start to attempt to solve. So the ground is lava. This is our ground. And we have our beautiful 25-meter tall cliff. This is our cliff. We know it's 25 meters tall. I don't want to overload y'all, so I'm actually going to include on the side a little bit. our cliff. No. The cliff right here is 25 meters tall. Okay, let's think about where this ball is going. So we have a ball right here, and we're told that it is thrown at 30 degrees. It's launched, right? And so we have this, and you kind of have to think about it going down to the ground. So that angle is coming from this point right here, right? At the height of that cliff. This angle is right here. This little angle right here. This is what we're talking about when we say that launch angle of 30 degrees. Let me open this up. You'll see it all the time. 30 degrees. We're also told that the initial speed is 45 meters per second. That's right here. See how it's not a matter of the actual y? It's not this, or it's not like that, but it's that resultant angle, right? It's that angle of literally that motion, like what you're seeing. This is the initial speed that the ball is going to be thrown at, and we call it VO, and it's 40 meters per second. Okay, so this is what we come to understand. This is what we've got so far. So this is all the drawing part. This is for all you visual people like me. This really helps me to see what I have and what I don't have. But I also like to reinforce it by listing what I know and what I don't know, so that when it comes to choosing the right equations, because we got so many of them, I know which equation I need to use. And so the second step I advise for y'all is to list what you know and what you don't know. I'm sorry this is a little long, but I think that it's good since there's no one that showed up. It's good that if y'all go back to this, you'll kind of see how I approach the question, and you can always play this video at 4 times speed. So I'm gonna list what I know in terms of the X factors. I'm gonna list what I know in terms of what I call the mid factors. And so these are the factors that are the same, whether you're talking about up and down or left and right, right? This is your time. That's always gonna stay the same. And so X, your mid, your high. So your X factors, what I'm talking about is, let's start with what they give us. So they gave an initial speed of 40 meters per second. This initial speed is not an X, it's not a Y. It's a resultant, right? Remember when we're talking about a triangle? We're talking about, this is our resulting velocity. We aren't talking about our X, we're not talking about our Y, but we do need to find these components likely, right? So our mid is initial velocity is equal to 40 meters per second. And our time, we don't know yet, okay? And that's what we're trying to find out. Our X factors, we don't know them all yet, but let's list what we know we should have. Okay, EOX, AX, which is always, as we talked about earlier, and in the slide early, is going to be 0 meters per second squared, because that velocity is not going to change, right? And our change in X, why did it do that? Our change in X, which is kind of the distance that's elapsed between the beginning and the end. And our Y factors, we have our initial Y component of our initial velocity. And then we have AY, which we know to be negative 9.8 meters per second, as said in the previous slide. And then we also have change in Y, which we kind of do know, right? Because we're told that this cliff is 25 meters tall. And so if you think about what it means when we say delta Y, we mean final minus initial distance, or initial, in this case, is Y, we're talking about height, right? If that helps you a little bit. So we're talking about final height minus initial height. When we think about where the ball is going to end up versus where it began, it's going to begin at 25 meters, but it's going to end up ultimately on the ground. So we're talking 0 meters. So we're going to do 0 minus 25. This gives you negative 25 meters. So we have this, yippity, we have this, but a lot of what we're missing is this, and this. Generally, in questions like this, guess what you have to find? You're going to have to find these components in order to kind of start solving, right? And there's multiple ways you can approach this. You can kind of approach it step by step and see what you need, or you can have it all laid out and then solve all of it and then kind of just answer the questions as you go, right? So I'm going to do a mix of both. I don't really know how I approach questions, but I'm going to start off by seeing what we need to solve for A, okay? So we're told that A component is, what is the flight time? That's what we're trying to find out. So what equations have time in them? I'm not going to always flip back, but in this case I will since we're at the beginning, right? So I kind of have to look at what I have and what I need in order to find out what equation I need, what equation I need to use. So I can either solve this problem in the X direction or in the Y direction, right? Since we're solving for time, time is one of those factors that is both included in X and Y. So I can choose to solve with everything on my left side right here or everything on my right side. But it's like two separate entities. You can't cross and mix and match. You gotta use one or the other. And if I look between everything I have underneath my X factors column and everything under the Y factors column, what I'm seeing is that I have a lot more information in the Y factors column. So I'm going to gravitate towards that a lot more. Since I have more information, I'm going to be able to get my answer a lot easier and use the right equations, okay? So we're going to be using our Y factors. I'm going to give it a little green highlight. We're going to be using our Y factors, okay? So if I'm looking for an equation that has time in it, I see this equation right here. And sorry, I have it pulled up in front of me, but you can always refer to your own, which is the equation that you've seen before. Change in X is equal to VO, initial velocity times time, plus half acceleration times time squared, right? But I want it to be solving for the Y, because as we said, we have four components in the Y direction. So I'm going to adjust this equation for Y. VOY times time plus half AY times time squared. See these subscripts denoting Y and see how time doesn't have it because time is shared by X and Y factors. Hence why it's a median, it's a mid value, right? So I'm almost there to where I need to be able to solve this part, this A part of this question, right? I think the question I have now is, I don't have VOY. Sorry, there you go. Find a cute color for y'all. Is I don't have VOY, so how do I get there? What I have to do is I'm gonna have to think about this triangle at the beginning, right? You see this triangle right here? This beautiful, beautiful triangle? What we want to do is think about it as a velocity triangle, right? Or velocity triangle is what I'm gonna call it. So I have my triangle like this. I know that this long resultant side, this hypotenuse, is 40 meters per second. I know this angle right here is 30 degrees. I know this is called VOY. And I know this is VOX. And this is when you use sine and cosine, right? I know in the equations before in the textbook, it says it's usually, what's it called? A sine angle, beta, right? For your VOY. So I'm going to use that same approach, A sine theta, okay, VOY. Whereas VOX is equal to A cosine theta. And so here, right here, A sine theta, is our A is just going to be our long side right here, 40 sine, and our angle. So that's our value. And here it's going to be 40 cosine 30. So we have those values. They're just kind of hidden and harder. I'm going to add this to our graph. I'm not going to plug it in, but you can if you'd like to. So we have, see how many components we have now. We have solved this triangle. So going back to what we're trying to solve at the beginning, let's plug it in since we should have enough numbers now. So if I plug everything in, I'm going to do, what am I doing? Negative 25 times 40 sine 30 times time, which we don't know, plus half times negative 9.8 meters per second squared times time squared. What you're gonna have to do is plug this into a quadratic formula, which makes it a little tricky because it's just annoying. Hopefully, I mean, I think she does say that your quadratic formula will appear. So I would always prepare for it, but I would recommend that you program. Let me show y'all. Okay. Search up Google how to program onto your calculator the quad solve. Quad solve is like right here. And then what happens is you just kind of scroll down on test day. And oh my gosh, annoying. On test exam day, you just pull up quad solve, you plug in your values for A, B, and C, and all you need to do on your actual exam is just write out the quadratic formula to show that you know how it goes. And that's the best way to do it. Okay. So I'm not going to plug it in for y'all, but I am going to set it up to where you can kind of see negative 4.9 t squared plus 40 sine 30. This is all one value, by the way. T plus 25 is equal to 0. And so the values you would be plugging in would be negative, negative 4.9, 30 sine 40 sine 30, and 25. And ultimately that should give you an answer. I think the only positive answer would be 5.08 seconds. And that's how you get there. It's the answer. I'm doing yellow. So I'm going to update my table now because I know it's 5.08 seconds. Copy and then plug it here. All right. Does it not allow me to make it smaller? I guess it doesn't. Oh. Very much noob, guys. Sorry about this. Okay, so let's move on to the second part of our problem, which is asks us what is the range of the cannonball. And range is just this fancy way to say change in X. So what I hope that y'all are going to notice a lot is that it's a lot of front loading. These types of questions that can be asked in your exam. If you put a lot of work into solving out all these variables that could be asked about, you're going to have it very easy when it comes to solving a multi-component problem, okay? And so I hope you're going to see it right here. So the next thing they ask is what's the range of the cannonball? And a good equation to solve for that is just, I think you've seen it before in the previous chapters for kinematics is it's just change in X is equal to VT. And we're just going to adapt it to fit our needs. Vx times t. So what did we talk about earlier? We said that Vox is equal to V final x, right? Because Vx, velocity in the horizontal component, is always the same, whether you're at the beginning or the end. And so with that in mind, I know I can use this value for that value for Vx, okay? So I do 40 cosine 30 times the time that we solved for, 5.08 seconds. I'm just going to underline what we use. Here we use this and we use this. Okay. I want to see y'all. I want y'all to see where I'm getting my numbers from because I think it's the most challenging part. Stupid Zoom and its time limits. Okay. And once I plug this into my calculator, I'm going to get 175.90 meters. Okay. See how easy that was compared to everything we had to do for the first problem? So I'm going to copy and paste this again. And I'll paste this. So that my next thing I'm gonna do is find the impact velocity. Oop, I didn't update this. This would be 175.98 meters. What we're asked for now is to find the impact velocity when the cannonball strikes the ground, and we need to include both magnitude and direction, okay? So what we need to do here is think about this overall ball, right? We're talking about when it hits the ground, right? We have this ball that's like yeeting out of the air and it's flying down. And as it's flying down, it's going to be creating a natural kind of triangle with the ground, if you think about it, right? This magical little triangle right here. And what it's asking for, what the problem's asking you for is the impact velocity, which is the final velocity equals what? So what we have again is a kind of a component issue, right? We have to use what we know to help us figure out this, what happens at the end. So what did we talk about earlier? We talked about how this VOX is equal to V final. So in this case, we know V final X. I don't know why I started writing it like that. V final X is equal to 40 cosine 30. Now we're left with another problem. We have to find out what V final Y is. And this one's a little bit more challenging because you're going to have to use kinematics. There's just not simply enough information for you to like figure out what it is without pulling in additional information. And so we're going to have to use kind of another equation to solve for that component, which we're going to then use to solve for that question, what the question is asking of us. And so in a way, it's a very two-pronged approach, right? Two-step question. So we have to use kinematics to solve for this. And how we do this is we think about, okay, what's happening, right? Look at the equations. If we look back at our equations, we see this equation right here. We need final velocity, but there's an equation where we can solve for it. We have initial velocity and acceleration and time, and we do have those factors, right? So you'll see this represented in your textbooks, I think, as v is equal to VO plus AT. We can just adjust it, right? V final Y equal to V initial Y plus a Y times T. And if you plug that in, you're going to get VOY right here, 40, as I would circle in red, 40 sine 30 plus AY, which is negative 9.8, times T, which is 5.08. And if you plug that all in, what you're going to get is negative 29.78 meters per second. So that is equal to V of Fy, but that's not even what we want, right? That's not what we're looking for. We still need to answer the question about this impact velocity right here. So V of Y is negative 29.78 meters per second. So we're going to descend. We have these two values, right? So now think about that triangle that we keep talking about over and over again, right? This triangle like this. When we think about this triangle, we think about the fact that we need to find this side right here, our V final. We already have a lot of what we need. Our V final Y, which we know is negative 28.78, and our X right here, which we know is 40 cosine 30, whatever that is, okay? And so all we gotta do is Pythagorean theorem, which states a squared plus b squared is equal to c squared, where c squared is our long side right here, okay? So if you put that all in, I'm running out of space, guys. I'm so sorry. I think I'll also be out of time by the time I do this. So I'm going to zoom in, right? So a squared, any side, you can use any side for a, any side for b. So I do negative 29.78 squared plus, I'll just solve it myself. 40 cosine 30. Sorry, I'm trying to make sure it's in degrees, not radians, because I've done that before. I was in radians, cosine 30. Oh my gosh, 40 cosine 30 is gonna get you 34.6 plus 34.6 squared is equal to c squared, right? So you do that, take the square root of all of this, you're gonna get c, which is what we want, right? And c is gonna be equal to, c is equal to vf, final velocity is equal to 45.68 meters per second. Okay, you might think we're out of the answer, we got the answer, we're done. No, we still need to find the magnitude. The magnitude is essentially this angle right here, i.e., what is this angle? And to find out the angle, we're going to be using inverse tangent. So that just means we're to find the angle. This formula you can also put in your sheets. Negative tangent inverse tangent over tangent is opposite over adjacent. So opposite over adjacent, right? If we need to find this angle, this is our opposite. This is our adjacent. So all we got to do is plug this into our calculator. Inverse tangent is equal to negative 29.78 divided by 34.6. And that should get you your answer of negative 40.69 degrees. So with these two in mind, you have your full answer. Okay. Highlight that. That's your full answer. Okay, I'm going to pause now to end this recording and start a new one before it kicks me out. But I hope that makes sense.